Great. Okay, so question 2 was to describe at a high level what this ER diagram is showing. And there were some students who talked about the number of entities. There's 3 entities. One is employees. An employee is defined by their social security number, their name, and parking lot. Policies are defined by a policy ID and cost. Those kinds of things are fine. But when I was saying to a person who doesn't know about ER diagrams and what they might say, you didn't like lose points or anything. It was just you were adding more than I would have expected. Basically, what I was expecting was to describe each of these participation constraints and maybe saying something about this weak entity. So I'll just go over these in this order. The first thin line here says that an employee can purchase 0, 1, or more policies. The second here says that a policy can only be purchased by one employee. So employees can't share policies. One employee could have 5 policies if he likes, but each one of those 5 policies belongs only to that employee. This third says that a policy can cover 0, 1, or more dependents. So dependents here, usually children. If an employee has 3 kids, all 3 of them can be covered by the policy. Or maybe he doesn't have kids or just doesn't want to cover his kids, then that would be allowable as well in this system. The fourth one says that a dependent can only be benefited or the beneficiary of a single policy. Actually, more than that. If a dependent is covered, then they are only covered by one policy. So, okay, and number 5 here is just saying that dependents. Yes, I'm recording the lecture. So number 5 here says that dependence is a weak entity, or that if a policy is removed, so must the dependent from the database. So there's lots of different ways of wording this. A dependent exists in the database only because a policy exists, or, there's lots of different flavors of ways that you could word these things. So long you hit all of these 4, you got full credit for this, and just extra, thumbs up from me for describing the weak entity. Any questions about this one before we move on? Okay. Then the third question This is the one where a lot of people lost a single point or just points here and there. So there were two ways that I would have accepted it. Up here is sort of a table form. So first, this is the using the fewest number of tables that you can. This employee's entity is represented by a single relation. You also had to not forget to list which are the keys to these entities. So if you just had, for example, this, then you would have lost a point for not saying what the keys are, because that's important in with relations. In particular, because some of these keys in the ER diagram can be fewer than the required keys in the relational model. As you can see here, in this table, I have p name being a primary key, or part of a primary key, whereas here this is a partial key. So partial keys don't really exist in the relational model. So this would have to be a strict underline. Anyway, the easiest one is this, employees. That's just taking this entity and creating a table with 3 attributes, the social security number being the primary key. This part, the purchaser and the policies, here I'm combining these into one table. So this says that a policy can only be held, can only be purchased by a single employee. And because of that, this policy ID, being the primary key, is sort of doing double duty. You could not have 2 employees. This. Let's see here. Right. So you could not have 2 policies being covering 2 employees. So this could not happen. So you don't need to make social security number a key. This policy ID being the key sort of enforces by itself the constraint. So this is not allowed. Enforces this constraint here. Where a lot of people lost a point was that because this is a thick arrow, that the social security number cannot be null. So here, if I wanted to change this, this is not allowed because a policy must have a purchaser. And so the not null here enforces that this situation doesn't happen. The last one here, and there's no other way to do this. I'll mention this down here. This purchaser relationship could be broken away from the policies relationship, but that's not the case with the dependence beneficiary. So this really has to be combined together in a single table. And here, both p-name and policy ID are a composite key, or a concatenated key, which I signified by drawing this sort of line between them. In addition to that, the policy ID cannot be null. That's also due to this thick arrow. And also for it being a weak entity. In addition, because this is a weak entity, you need this on delete cascade note. That is to say that if see. If John, who's 11, is covered by this policy, and now this needs, and this policy gets deleted, then this dependent must also be deleted. That's as a consequence of this being a weak entity. So if the key here, policy ID, if the entry that this points to gets deleted, then this entry must also be deleted. Do you instead put social security number and policy ID in the purchaser relationship table? Yes, that is another valid answer. Do we have to write text decimal types in chart form? Yes, you should. Yeah, because the relational model is defined by a schema. So the schema is both the name and the type. Now, I don't really care what the type is. If if here I use text for the policy ID, if you used a number, that's fine. Cost, if you used an integer instead of a decimal or a real number, that's fine. But yes, the relation should have some type. Okay, so here this is in sort of table form. It's just this exact thing up here, but written out in table form. You'll see the employees table has here the social security number, the name, the lot, and the primary key being a social security number. Here I've combined the policies and purchaser entity and relationship into a single relation. The policy ID, one thing is, well, okay, so there's the policy ID, there's the cost, and the social security number. And this should have the not null. Again, this not null is needed because of this thick arrow that any social security number, if it's null, then that violates the fact that a policy must have at least one employee purchaser. Yes, this on delete no action, I just put that for fun. That's the default. That is that's implied. Yeah, that's the default. I just wrote it here just because. And if you put something else here, like on delete cascade, I didn't take away any points or anything for it. But yeah, the only on delete that you need is here, and the dependence beneficiary. There were some students who didn't have, who, for example, would put something like this, where they would have the policy ID, the cost, and the primary key, and then they just sort of defined this foreign key, social security number. But you can't really do that. You have to actually specify this as being an attribute as well. So each of the keys are also attributes of the relation. And for the dependence beneficiary table, again, that's sort of, this has to be one table. The reason for this is, well, I'll mention that in a minute. The main points were that you need the, sorry, this should be p name. That you have the p name and the age from the dependence relation, as well as the key that it relies on, the policy ID, and that cannot be null. The primary key is the concatenation of these, and that's important. It can't just be one or the other. It has to be both. And this as well, on delete cascade, as I mentioned above. Now, another solution to this would be, you could break apart the policies and purchaser relationship and have a policies relation that just covers the policies entity, in which case there's only two attributes, the policy ID, the cost, and the policy ID is the primary key. And then the purchaser table has two attributes, social security number and policy ID. Excuse me, this is with just the policy ID as the primary key. And both the SSN and policy ID are foreign keys referencing their respective relations. Again, you need this not null for the social security number. Now, the reason why you can't break apart in the same way the beneficiary table, the dependence is really where this is a problem. If you wanted to have a dependence table with P name and age, then the only way, you need some primary key. So if you tried to make dependence its own table, then P name would be a primary key, which means that you could have no repeats. And that is not the case with a weak entity. You could have multiple dependents with the same name. The way that they'll be differentiated is by the social security number that they're tied to. So, yeah. Can you also use P-name policy ID? Oh, yes, I'm sorry. So, yeah, I'm sorry. There should be no social security number. Yeah, so the dependence beneficiary table, there's no social security number involved in this relationship. It's sort of implied indirectly by the way that everything else connects together. So this primary key should be P name and policy ID. Yeah, sorry, that was a mistake on my part. Okay, and as far as question 4, that was just really very dependent on everybody's own take on the question. So, yeah, I'd say if for people who lost points, it was mostly on questions 3 and 4. There were a few people who missed some points on question 2, but overall, people did very well. If you have any questions about why you received the grade that you did, you can, ask me during my office hours or something, and I can share the screen and go over your homework with you. So that's it. If there's no other questions, then we can continue on with relational algebra. Yeah, so this is something that I'm still thinking about. It really depends on how quickly we're able to cover all of the material that I want to. So there's some parts of relational algebra that I think are important as far as wrapping your head around how to break down queries into the relational algebra query. And I think that that's easier than just jumping straight into SQL with it. So right now we're discussing relational algebra. I'm guessing that we won't finish today, but we should finish by next Tuesday. And then I want to go into SQL. What I don't want to do is to leave you guys with 1 week to do a project. That just seems like it would be a really crappy thing to do. So I'm thinking about it. If somehow, I can push back the final somehow, or have the project be something where I feel like you could spend a week on it and have it be something that's manageable, then I'd like to still do it, just because I feel like that would be a nice application to walk away from this class with. Originally, I was hoping that it would be the type of thing that you could put on your resumes, that you've worked with cloud services and actually have experience with some web servers and querying an actual database, instead of everything just sort of being on paper. But I haven't quite made up my mind yet about that. I'll let you know by this time next week. Yeah, if I'm able to start, yeah, it depends. I guess I'll keep you guys in the loop with this, and any decisions regarding it will hopefully favor you guys. So, as far as grade weight distributions and things like that. Any other questions? How would you get into teams for the project? Yeah, if we do the project, then it would be either you can choose your own teammates, or otherwise, if for whatever reason there's students who are having trouble with it, then I could help match people up. But if there's people who already know each other and work well together and who would like to be on a team, that seems like um, something to encourage. But like I said, if there's students who maybe don't know other people in the class or would like, then I'll try to match up remaining people. So, for example, maybe if there's some people who know who have some experience with a little bit more Python experience, or working with web servers or something like this, then pairing them up with somebody who feels more comfortable with the database things, that would also be a good pairing. But I guess, yeah, maybe we'll cross that bridge when we get to it. Okay. So I won't go over, again, all of the examples that we've been working through. I did upload each of the examples that we've worked through so far to Blackboard, so hopefully that's there for your reference. But part of this is going to play into some later examples that we have. So I wanted to come back to this example 4. And with this type of phenomenon, so this is taking a set difference. And the reason why we take the set difference is because of this word in the query that we want to achieve. Find the restaurants that are frequented by only females. And the problem with this, and the reason why it requires doing a set difference, is because you have to break down queries to be such that they can be achieved by checking relations one entity at a time. And as you're checking each of the entries in the entity, the database only has the memory of what it's looking at in that entry at that time. So it would not be able to go through the person and the frequents table and showing that this restaurant is frequented by this person is a female, so far so good, let me remember this restaurant, and now I'll check the next entry, and if it's the same restaurant, then it's a female, still so far so good. That type of logic doesn't work in databases. So in order to achieve this, we had to change it into something that can be checked in this. You only need the memory of a single entry type of query. And this is changing, it's actually changing a quantifier. And I'll get to that in a little bit. But I wanted you to remember this example. So the way that we achieve this is that we can look for restaurants that are frequented by at least one male, and we can come up with a list of those, and then forming this sort of red circle. And then we can also check for the entries of restaurants that are frequented by at least one female, getting sort of this green circle, and by taking the difference of them, you're left with logically restaurants that are only frequented by females. And this is the reason why we do the set difference. The key here is this word only. So, okay, I just wanted to have that in your mind before we get to the very last example that we'll be spending a good chunk of today on. Let's see here. Great. Okay. So this is no more complicated than the example we were just looking at, but it's related to that kind of logic. So here, the query is for each person to find, to return all the foods, or to return these pairs, person-food pairs, that the person eats that are not served by any restaurant the person frequents. So each person has a list of foods that they eat, and this should return the restaurants that this should return the people and the food that they eat that is not on the menu of the restaurants they frequent. So I put some sort of, I filled out some of these tables. And first I just wanted to ask you, given the data that are in these relations, what should this query return? So without specifying the relational algebra expression, just given this data, what should the result be? Okay, we're getting different answers here. Correct, that are not served. Okay, I'll just take, I don't know. Dan, do you have a microphone?
Can you hear me?
Yeah.
All right. So just explain.
Yeah.
Well, so John frequents McDonald's and he likes chicken and pizza, and chicken and pizza is under Fridays. So if I'm reading it correctly, John chicken and John pizza should be returned. And then Peter frequents Fridays and Peter likes salad, and salad isn't even on the restaurant serves list. So
Mhm.
Peter salad should also be returned.
Excellent. Okay. Perfect. That's right. So, it's yeah, the way that I think about this is that I have a list of foods that I like, and then I receive the menus of the restaurants that I frequent, and I cross off from the list of foods that I like if I find them on any menu, and the result is whatever I have not crossed off my list. And you do that for each person. Um, okay, great. So, yes, let me just copy one of these. Okay. So that's just a note for you. All right. Now, I would like to give you guys a few minutes to try to think about how to tackle this with relational algebra. Um, I was going to ask, would you like to, I don't know, throw around some high level ideas first, or would you just like to have a few minutes to try to work through it? I'll go with sort of whatever the, have a few minutes to try to think through it. Okay, great. Well, I will share this timer app and give you guys 3 minutes, I guess. Okay. Any ideas? Okay. Let me give myself some space here. So we have pi name of a pi name and food eats. I'll start writing it. In the meantime, Jamie, can you tell me what you mean by and? Oh, I see. Pi name. Oh, my name here. Food eats. Minus pi name and I'll name food. Sigma. Restaurant equals restaurant 2 frequent cross row restaurant 2 of serves frequent like this. Excellent. Okay. Yeah, this is correct. Good job, Jamie. I will mention that this pi isn't, it's sort of redundant. I mean, eats already has name and food, so you don't need it. So just to try to keep things simple, I'll get rid of this. And Jamie, do you have a mic? Can you unmute yourself and explain how you came up with this?
Can you hear me?
Yeah.
Okay. I was having mic trouble earlier in a different class, but anyway, I did notice that the eats table already has name and food. I put the pie because I didn't know that you had to specify a way to return it, but then to get the other part, I knew that if we combine the frequents with serves, we'd get every combination of, I guess in this example, John and Peter with the restaurants that they go to, and then you'd have them paired with every type of food that that restaurant has.
Mm-hmm.
Then if they show up with a food that's in the eats table and we did the set difference, it would subtract it out.
Excellent. Great. Yeah. So this part that I've sort of commented on in green is coming up with a list of the names and the foods that are served by restaurants that people frequent. So this is if you have the list of all of the foods that people like to eat, and you remove from that all of the menu items from the menus of the restaurants that they frequent from the list of all their foods, then what you're left with are the foods that aren't served. So, let's see if I can do this. So this is list or foods people eat. And this is foods served by restaurants frequented. And if you subtract one from the other, what you're left with is the foods that are not on the menus. So there's some overlap here. There might be foods that they aren't, that they don't really like that are on the menus. That this part is actually is just this part. Oh, sorry. Oh. Foods served by restaurants frequented is this. Okay, maybe I'll do this in blue to try to keep the color scheme. Yeah, so this is basically what this query is doing. Okay, excellent. Any questions about this? I'll take your silence as a no. Okay, so it looks like we won't have time to get to this example, but I'll show it to you anyway. Find the names of all people who frequent only restaurants serving at least one food they eat. So these are people who will only go to restaurants if they have something that they like. Seemingly simple statement, but this is going to be a relatively complicated query. And I spent some time trying to think about how you can arrive at the query itself. And I could give the answer and it would make sense, but the hard part is trying to come up with how to derive it yourself. And so for that, I decided to spend some time talking about what's called quantitative reasoning. I have put a set of notes up by one of the professors in the business school, Pericles Papakonstantinou, who kindly said that I could share them if I like. And it goes over this topic, quantitative reasoning. There's 3 parts to it. It's about 30 pages altogether. Really, this concerns the third part, so roughly 10 pages. It's not required reading, but yeah, I think it's something that would be beneficial for you to go through. So, I assume that you've seen at least the first 3 of these things in your Introduction to Programming class, but I thought I would go over them again quickly anyway. So the first three, these are called logical operators. And the way that, one way to, put out how they work is with truth tables. So here, a 1 will correspond to true, and a 0 will correspond to false. And I'm going to be making what's called a truth table. So if you have two variables, x1 and x2, and x1 and x2, by the way, an and is written like this, an or is written like this. I've already used these, but I'm just showing you. And a not is like this. So if you have two variables, they can both be false. One of x2 can be true and x1 false, x1 true, x2 false, or they can both be true. And x1 and x2 is true if and only if both of them are true. So I'm not spending a lot of time on this, again, because I think that you've seen it before, but if you want me to go slower, just say something. So the first part's the same. These are all the possible truth values. And for x1 or x2, this is true if either one of them are true, including both. So that's not always the way that it works in English, but in logical reasoning, this is the way that an or operates. It's true if both are true. Okay, and not is pretty straightforward. It just flips the value. Okay, just out of curiosity, how many of you are familiar with De Morgan's law? Looks familiar, yeah. Okay, let's see. Leora, do you have a mic? Okay, then how about Matthew?
Hello?
Yeah. Okay, so yeah, what is De Morgan's law?
So it goes something on the lines of like you can make a negative out of these statements by having like the change in them. It's I've seen it done with like logic gates, but I don't know too much about it. But it's obviously it's in the vein of what you're doing.
Yeah. Okay. Great. Yes. So that's part of it. Yeah. Leora, does your sound stopped working for a bit? Yeah. Do you have a mic?
Can you hear me?
Uh-huh.
Okay. Sorry, my WebEx has been giving me a lot of issues today.
Yeah.
So De Morgan's law. Do you just want it in terms of like what it like? Do you want me to just give it to you?
Yeah, that or an example or whatever.
I can just give it. So if you have like the negation of P and Q, then that's the same as the negation of P or the negation of Q.
Great. Okay, thank you. Yeah, so here P, Q are predicates. Where this just means a true, false statement. Or you can think about it as a true or false variable. So De Morgan's law just says how you distribute nots in statements. So here, if you have not P and Q, then this is the same as not P and not Q. So the not flips the P to be false. The not changes ands into ors. And the same thing, the not applied to the Q gets not Q. And similarly, let me put this over here. Similarly, if you have P or Q, then the not of that is not P and not Q. So here, I have some statements. We will go to the park if it's the weekend and it's sunny. So this whole thing is a true-false statement. You either will go to the park or you won't. And that will happen if it's the weekend, which is true or false, and if it's sunny, which is true or false. So I'll call this P, and I'll call this Q, and P, Q, and then we have P and Q. So this will just be the same and table as above. Oh, some more. Okay. And now we're going to see what not P, not Q, and not P or not Q is. So here, we'll do the same. These are the possible truth values of not P and not Q. And because we're ORing them together, then 0 and 0, or 0 or 0 is 0, 0 or 1 is 1, 1 or 0 is 1, 1 or 1 is also 1. So, let me move this over a little bit. Okay. We extend this table to not P and Q, then that just flips each of these bits. And you can see that both of these are the same. The order is mismatched because here let me just reorder these. So going from this table on the left, if P is 0, then not P here is 1. If Q is 0, then not Q is 1. And we'll just work like that. So then this is our OR. And as you can see, they are identical. So this and this are the same. Okay, so using words, we will go to the park if it's the weekend and it's sunny. So if you did not go to the park, that means it was either not the weekend or it was not sunny. SQL support the 8 common logic gates. You might have to tell me what each of the what the 8 common logic gates are. And, or, not, X, or, what, nor? Yeah, Matthew, maybe you can get back to me after class. So, I will, let's see. We only have 3 minutes left, so let's see. I will leave this for you as an exercise to show that this is true, that in the same way that I went through this example, it's pretty symmetric to come up with this on your own. Certainly some of them. I'm not sure about things like X nor. I'll check on that. I'll get back to you. Okay. Then these, there exists and for all. There exists is signified with this sort of backwards capital E, and for all with this upside down capital A. So these are called quantifiers, and there's only 2 of them. So there exists are for statements like if you're talking about the existence of something or not, there exists a meaning to life. There exists a cup on my table. There exists pigs flying. These are statements where you have a collection of things, and you only need one of them in order for this to be true. There exists. So it's a statement that is applied to a set of things, and it is true if you take this statement and you apply it to every member. So you look at this and see if it's true for that. You look at the second and you see if it's true for that. And you do that for every single item in the set. And if it's true for just one of them or more, then the entire statement is true. And for all is something similar. I mean, for it just has to be true for every single one of them. So this, you still take the statement and you apply it to every single member. And in the case that every single one passes the test, then the for all statement is true. These can be combined. And I will leave this, I'll pick it up from here next class. So I'll skip the De Morgans. I'll leave that for an exercise for you to complete. And next time I'll pick it up showing how these, things have statements like for all something there exists, something such that, something or there exists, something such that for all something. This is one example of that. There exists a day this week such that for all hours it rained. But I think that getting through this is going to make these more complicated queries, it'll give you a systematic way to figure them out. So that's it. Thank you, everybody. And I will see you on Tuesday.